In the first propositional logic lecture and the little logic connectives video, we covered the formal system of propositional logic, logical connectives, how to symbolize simple statements, how to use parentheses to make more complex statements. And we learned a whole bunch of rules for helping us translate more complicated, nuanced English into our simple formal language. Now we're going to turn our attention to our effective decision procedure. Right? So we have a decision procedure that allows us to determine whether or not any given argument in propositional logic is in fact valid or is in fact invalid. It's effective because it will give us an answer for every argument, and that answer will be correct. Our decision procedure is called truth tables. And truth tables are a graphical proof procedure. They show us why an argument is valid by showing us every possible way the world could be, so that we can see the argument is valid in every different possible way the world could be, or conversely showing us a way the world could be where the premises would be true and the conclusion false. In order to use our effective decision procedure, in order to use truth tables, we're going to have to get definitional truth tables, and we'll have to know these truth tables. They tell us what each of our compound statements says, the truth value every different way the world could be. And then we'll have to use those definitional truth tables to construct truth tables for the various statements and arguments that we want to evaluate. We'll see the truth tables are a very versatile procedure. We can use truth tables to determine what kind of individual logical statement we have. Is it a logical truth, a logical falsehood, or is it a contingent statement? We can also use our truth tables to determine whether or not two statements have a number of important different kinds of relationships between them. So we can decide whether or not two statements are logically equivalent to each other, whether they are contradictory statements, or whether they are either consistent statements or inconsistent statements. And we'll talk about what each of those terms means as well. And then finally, we'll look at using our truth tables to decide whether or not an individual argument is valid or invalid. So, as I say, truth tables are just a graphic means of laying out every possible combination of truth and falsity for every constitutive simple statement in our argument or our formulas. So every different possible combination of truth and falsity for each of those individual constitutive statements. So it's very mechanical to the point of being sometimes a bit tedious, but it's also very powerful. It's a systematic, mechanical means of exploring all the possible combinations of truth and falsity for any formula or formulas. And when we do that, we're able to test relationships between formulas, determine the kind of formulas we have, and we can determine whether or not an argument is valid or invalid. In order to do that, we're going to have to learn our definitional truth tables. And definitional truth tables are just truth tables that tell us the truth value for any of our statements, our complex statements. So, for example, here we have our definitional truth table for the tilde. Here we have P, that's our simple statement. P is over here, and here is tilde P. Underneath each of these, we have the truth value possibilities. This is called our guide column. Right? Up here in the top left-hand corner, we put all of our simple statements. Down here, we put all the combinations of possible truth values for our simple statements. Up here, we put our formula. under each element of the formula is the truth value for that element, and under that connective is the truth value for the whole statement. So under our tilde here, we get the truth value for tilde p for every different possible way the world could be for p. So if p is true, tilde p is false. P is false, tilde p is true. And so we can learn these definitional truth tables because their information can be expressed in a simple sentence. So the truth table for tilde p says every truth value is the opposite of what the tilde negates. What about our triple bar here? Well, again, here are every possible combination of truth values for our simple constitutive statements. Statements here, truth values here, these are called our guide columns. Up here we have our formula, and down here we have the truth values for each of these constitutive statements and for the whole formula itself. So under that triple bar, we've got the truth value for P triple bar Q, every different way the world could be. So if they're both true, it's true. P is true, Q is false, false. P is false, Q is true, false. Both false, false. So our rule for the triple bar is always going to be true when they have the same truth values, always going to be false if they have different truth values. Here's our dot. Our dot, our rule for that is only true if both statements are true. So it's true when they're both true, it's false otherwise. Or horseshoe, our conditional statement, it's going to be true when the antecedent is true, true when the antecedent is false, and in fact the only way to make a conditional statement false is if the antecedent is true, the consequent is false. Finally, our wedge. Our wedge is inclusive or. It will be true of one or the other, or both of the simple statements are true. So the only way to make the wedge false is if they're both false. So again, our tilde, opposite truth value of what it negates. Our triple bar, true when they have the same truth values, false when they have different. Our dot, only way to make it true is if they're both true. Our horseshoe, the only way to make it false is if the antecedent, the left-hand side, is true, the consequent, the right-hand side, is false. And finally, our wedge, the only way to make it false is if they're both false. So we'll use these definitional truth tables in the next module.